like what we saw so far is like sequences of operations. What we put in that chain is like the output of a layer or of a function is the input of a subsequent layer. In general, neural networks are graphs. They are technically directed as acyclic graphs. Acyclic, never remember how you pronounce that. And that means I cannot, like, if I look at these as an example, I cannot take the output here and fold it back in. Yeah. But we have already seen something like this. Something like, for example, this H here with our loss layers. The loss layer takes the predicted outcome, the actual outcome, and computes some form of distance between the two. So that's kind of like in a single node, something like this. But yeah, in general, I can connect layers in this way. Like a very common structure, for example, that you're gonna see is to model instead of learning like functions directly, like what is I have x and I learn f of x. You can write a function like this, saying like my x goes to 1 plus or actually sorry, x plus f of x. And the idea here is that your function now is a perturbation of the identity. And so this is a graph, of course, because I have to send my x to a function and then send the result of this function and the original x together. So I have like kind of a little ring that like a bifurcation, and then it goes back together. And this is a nice structure. is very used because is a lot more stable. Because I guess it's simpler to learn a zero or something close to zero if you don't have to do much than to actually learn an identity function. And this stabilizes the training a lot. So like this is kind of a very kind of trivial application of the fact that you can have bifurcation, but is actually a very used and useful one. So let's look at problems that we can solve with graphs. Oh yeah, see here, I forgot I put this in a slide and I gave the same example. So this is the way to re-implement mean squared loss using a net graph. So what I do is I use like a spreading layer, which is basically it's like elementwise, but between two arrays instead of one array, and you subtract. And then I use an elementwise layer that does the square, which is this one. And then I use an aggregation layer that is basically collapsing one axis of the array. Actually, in this case, all axes of the array. And I say use this operation to collapse them, which is mean. And in this case, this is quite a simple graph. But this is the explicit version of my mean square loss layer, and you can see it gives exactly the same output. Of course, in general, you want to use actual layers when they are available because they might have some optimization inside. In this specific case, I don't think there's any difference. But in general, you want to stick with the named one if you find it.